Okay, so let's get started, please. So today we are going to finally talk about the singular value decomposition, which is one of the best results along the lines of applied math that we're going to get this term. Okay, so 6.5, constructing a singular value decomposition, of a matrix. Constructing a singular value decomposition of a matrix. And I think I said this last time, but this is sort of like a generalization, well, look at all these pens. Sort of a orthogonal diagonalization for rectangular matrices. Okay, so right, if you have a symmetric matrix, so recall that if you have a symmetric matrix, then it has an orthogonal diagonalization. Okay, any symmetric matrix has an orthogonal diagonalization, and this is going to use that. Okay, but let's start off with a warm-up exercise. So this is from section 5.2, number 13. It goes like this. Suppose you start off with an m by n matrix. Part 1 says if x is in the null space of ATA, then AX is in the range of A, and it's also in the null space of AT. If x is in the null space of ATA, then AX is in the range of A, and it's also in the null space of AT. So, just to get your minds going again, I don't know if they stopped over the weekend, but get them going. Take 1 minute and see if you can get this. This is actually pretty straightforward, so it should not be hard. Okay, talk with somebody nearby and say, it's easy, or of course, or it is trivial, it is trivial. There was a graduate student from Greece when I was doing my PhD, and he had the answers to everything somehow. Whenever we asked him questions, he would say, it is trivial. It's trivial. And so we all try to imitate him. It's trivial. Yeah, he was smart. Okay, nobody's talking, so maybe you're not awake. But first off, so we want to show that AX is in the range of A, and it's also in the null space of AT. Well, AX is definitely in the range of A, right? Because it's AX, right? right? It's A times X. So by definition, it's in the range of A. So this part really is trivial, right? AX is definitely in the range of A because it's A times X, right? So this is sort of by definition. Okay, is AX in the null space of AT? So in other words, if I have AX and, in other words, is AX, if I multiply it by AT, do I get 0? Yes, because we said X was in the null space of ATA, right? X is in the null space of ATA, so AX is in the null space of AT. Okay, so this really was, yes. This really was simple. X is in the null space of ATA. Okay, so this first part A was really actually very simple. Okay. Part B, show that the null space of ATA equals the null space of A. Okay, so we'll do this in two parts, showing that the null space, that's an equal sign, in case you didn't hear it. We'll show that the null space of A is contained in the null space of ATA, and then that the null space of ATA is contained in the null space of A. Okay. Okay. So can anyone just look at this and tell me why, if you are killed by A, right? If you are a vector that A sends to 0, why does that mean that you are a vector that ATA sends to 0? Right? If A kills you, why does ATA kill you? Dan?
Because A times the vector equals 0, then A times 0 equals 0.
Exactly. Right? So certainly if AX equals 0, then ATAX is going to be AT times 0. Well, that's just right. So if you're killed by A, you're definitely killed by ATA. Okay. 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 Now let's do the other direction. Suppose that say X is in ATA. Oops, the null space of ATA. Let's not say anything meaningless today. Say X is in the null space of ATA. Well, we just got something that AX then by B, AX is in the range of A, and it's also in the null space of AT. Right? That's what we got. That was the simple thing we got in part 1. Okay, does anybody remember the fundamental subspaces theorem? The range of A equals the, anybody remember? It's been a while. Russ.
So perp of null space of AT.
The perp of the null space of AT, exactly. The perp of the null space of AT. Okay, by the fundamental subspaces theorem. And so you see that AX is in the null of AT perp, and it's also in the null of AT, so it must be 0, right? The intersection of a subspace and its perp, its orthogonal complement, right, is just the 0 vector. Okay, right? So that means that X lies in the null space of A, right? Because AX equals 0, right? AX equals 0, so X is in the null space of A. Okay. Okay, so so being in the null space of ATA implies that they're in the null space of A, right? So we see that these two guys actually are the same. All right, part C, show that the rank of A and the rank of ATA are the same. Okay. I don't want to use too much time, so I'm going to do it. Let's do it together. We know that B says that the null space of ATA equals the null space of A. Take 10 seconds and write down what the fundamental subspace theorem says about each of these things. Right? The null space of ATA equals the null space of A, then what do you know? Okay, anybody want to tell me? Anybody want to tell me? What does fundamental subspaces theorem say? Well, it says that this is going to be the perp of ATA transpose, right? But what's ATA transpose? What's ATA transpose? ATA, right? ATA is symmetric, right? ATA transpose is A transpose ATT. In other words, ATA again, right? Right. Okay, so we get the perp of ATA transpose, which is just A again, right? And then here, fundamental subspaces theorem says that this is going to be that, right? Right, the null space of A is the range of AT orthogonal complement. Okay, so this is what we get from B. Right, B actually says this. Okay, and then what am I going to do? I'll say I'm going to take the orthogonal complements of both sides. Right, these things are equal. So I'm going to take the orthogonal complements of both sides. Right? I'll get this thing perp. Well, we had a theorem that said if you take two perps, you return the orthogonal complement of the orthogonal complement is the original space. Right? So this is going to come back to just ATA, and this is going to come back to range of AT. Right? Right? Because we had some theorem that S per perp equals S. Okay, so we get this, that the range of ATA and the range of AT are the same. Okay, but that means that we can get this, the rank, right, the dimension of the range of ATA and the dimension of the range of AT are the same, right? So this is the rank of ATA, and this is the rank of AT, right? So you might say, but we wanted the rank of A. We're okay, right? Because the rank of AT is the rank of A. Right? The rank of AT and the rank of A are the same. Right? The dimension of the column space and the dimension of the row space are the same for a matrix. Okay. Okay. Everybody okay with this stuff? This is just, stuff from chapter 5. that we're going to use a lot of when we're constructing the singular value decomposition. Okay, it turns out that we've got this. We have in the singular value decomposition, we're going to have some rectangular matrix A, right? We'll be dealing a lot with ATA, okay, which is a symmetric matrix related to your original matrix, and this ATA contains a lot of the information of A, basically. So that's the idea. Okay, so we need these various facts that are in the boxes. Right, maybe I should box them over here. The null space of ATA is the null space of A. The range of ATA, of course, the range of A transpose. The rank of A is the rank of ATA. Okay. So now put on your hats. Let's go. Let's do the singular value decomposition. So singular value decomposition. Whoops. Singular value decomposition. SVD. Okay. So let's talk about what it is. Okay, so let A be an m by n matrix with where m is bigger than n. Okay, so the number of rows is bigger than the number of columns. It's a tall matrix. Okay. If there exists a matrix U that is in OM, that's to say the orthogonal m by m matrices, okay, and a V in ON, and a sigma in, that's just an m by n matrix, such that A equals U sigma V transpose. Right. V transpose, remember, is the same thing as V inverse, right, since we are orthogonal. Then we call U sigma Vt a singular value decomposition of A. Okay, leave a lot of space here. Okay, I left a lot of space here. Leave a lot of space because this is not the full definition. Okay. Well, people are still copying. I'll take time to erase. Okay. So first pass through, right? You've got an orthogonal matrix on the left. You've got this orthogonal matrix on the right. Right, orthogonal matrix, and then this thing in the middle, right? So you've got orthogonal matrix, inverse of orthogonal matrix, and then this thing in the middle, right? So this should sort of look like the spectral theorem, right? Spectral theorem says that if A is symmetric, there's the real spectral theorem. Real spectral theorem. If A is symmetric, then there exists a orthogonal Q such that QA Q inverse or QA QT is diagonal. Okay, so this is something like that. Okay, you can break your thing up into this thing. There's something in the middle. There's orthogonal matrices on the left and right. Okay. Okay, so let me put in the details. So we need to say something about this sigma. And sigma is no. And the upper n by n matrix of sigma is diagonal. And the rest of sigma is 0. Sorry. The upper matrix is diagonal with decreasing entries. Sigma 1, sigma 2, through sigma n. And sigma is 0 elsewhere. 0 elsewhere. Then we call this thing a singular value decomposition of A with singular values sigma 1 through sigma n. Okay, so right, this sigma is also an m by n matrix, right? It's a tall matrix, the same size as A, and the way it's going to look is it's going to have right this part up here. This is there are it's an m by n matrix, right? And what we're saying is that this top part is diagonal, and then it's 0 elsewhere. Okay, so this is very much a diagonalization result. Okay, we're saying that you can take your matrix, and then you can take your rectangular matrix, and then diagonalize it with orthogonal matrices. These orthogonal matrices will not be, this U is not equal to V. It can't be because you've got the wrong sizes, right? One is an m by m, the other is an n by n. Okay, but they're going to be closely related. There's going to be a relation between them. Okay. Okay. So I don't know if this helps you, but let me just put up. So later on, we're going to calculate. We're going to have something like this. We'll do an example later on. We'll take a matrix, okay, and then we'll do the singular value decomposition on it, and we'll get something like this. So that in the middle there will be a diagonal matrix. On the left we have an orthogonal matrix, and then on the right we have another orthogonal matrix. Transposed. Okay. So later on, we'll see how to do this. We'll take some matrix and then we'll get a singular value decomposition. Okay. You see, it's not exactly like the diagonalization, but it's kind of similar. I don't know if that helps you. Okay. Anyway, this turns out to be a very useful thing to do. So you're probably like, why? It doesn't seem useful. What's so great about this? But I think I mentioned last time. Did I show you the book last time? Right, the picture, like getting low rank approximations. That's all this. Okay, so often to get to something useful, you have to go through a fair amount of actually mathematics. So okay. So that's just what a singular value decomposition is. Okay, and now we have to say, like, how do we get one? Okay. So singular value decomposition is just something that looks like this. It's a sort of like you get this diagonalized rectangular matrix in the middle, and you get orthogonal matrices on the left and right. Okay, one transpose. Okay, so construction of the singular value decomposition, kind of intricate. So here's the theorem. Every matrix has a singular value decomposition. It's not unique. It could be multiple. It can be tweaked a little bit, but they're all kind of similar. Okay, so we'll construct it in two steps. Okay. The first is we'll construct something called the compact singular value decomposition. Okay. It's some sort of baby version of the singular value decomposition. Okay. So this will start off with a couple of observations. So observation number one is that ATA has real non-negative eigenvalues. ATA has real non-negative eigenvalues. Okay, I should say that we're going back to the world of real numbers again. Okay, so we're not talking about complex numbers here, just real numbers. So right, this is in Rn, not in C. This is a real matrix, not a complex matrix. Okay, so why does it have real non-negative eigenvalues? Say, well, okay, well. Suppose lambda is an eigenvalue of ATA. Then we know that ATA V equals lambda V for some V. Oops, for some non-zero vector V. Okay. That's what it means. It could be an eigenvalue. Okay. And then, if we look at lambda VV, okay, and this is back to the real inner product. This is not the complex inner product. We're going to use this for the real product now. See that that's the same thing as I can pull the lambda inside. Right. That's the same thing as ATA V lambda. Right. the same thing as AV, AV. Right? Because of the definition of the dot product, remember? Right? This is V transpose ATAV. This is AV transpose AV, and those are the same things. We get V transpose A transpose AV, which is this. But that tells me that lambda is AV, AV. Lambda is the norm of AV squared over the norm of V squared. Right? Get the norm of AV squared, divide by the norm of V squared, you get lambda. Right? Okay. Well, that's positive, right? But it's not negative. Right? These are real numbers, and these are, the bottom is not zero, the top, it's at bigger than or equal to 0. So you get that ATA has real non-negative eigenvalues. Okay. Say that there are, arrange the lambda in decreasing order. So lambda 1, beginning to lambda 2, etc., etc. Okay. And suppose that at some point they become 0. Right? There should be n of them. Right? There's going to be n eigenvalues. Some of them might be the same, but let R be the number of non-zero eigenvalues. So these guys are all non-zero, and then past that point, those guys are 0. Right, so R is some number between 1 and n. Okay. Okay. Okay, so the rank of ATA equals R. It's going to be the number of non-zero eigenvalues. So the rank of A is also R because of what we did earlier. Okay. Okay. So now we enter sort of a second phase. Observation number 2. Notice that ATA is symmetric. AT is symmetric, so by the spectral theorem, we know that there exists an orthogonal V, right? What are the dimensions of ATA? A was an m by n, right? ATA is going to be a n by n, right? ATA is going to be an n by n. So you have this, there's an orthogonal n by n matrix called V, such that V transpose ATA V is diagonal. Okay, hang in there, hang in there. So remember what we're doing? We're constructing the singular value decomposition. Okay, so this is, this is, part of the, we'll get there pretty soon, don't worry. We've got 12 minutes, we'll do it. Okay, so, so this guy is symmetric, so it's diagonalizable, right? It's orthogonally diagonalizable. It's gonna be D, right? What's D gonna be? What's D gonna look like? It's diagonal with
upper triangle.
It's actually diagonal. It's just
only diagonal.
It's truly diagonal by the spectral theorem, right? Any symmetric matrix is going to be diagonalizable. So it's going to have, what is it going to have down the diagonal? Well, it's going to have the eigenvalues down the diagonal. Okay, so it'll have lambda 1, lambda 2, lambda r, and those guys are all non-zero. But then afterwards, the other ones are 0, right? So it's going to look like this. So this is an n by n matrix. It's an n by n matrix. It looks like this. I mean, really, there's lambda r plus 1 through lambda n here, but those are all zeros. So I'm going to ignore them for now. I'm going to ignore them for now. Okay. Okay. So call this guy, this r by r matrix. Let's call this guy lambda 1 squared. I'm sorry, sigma 1 squared. Okay. So that is, if I write sigma 1, what I need is this guy, where you take the square roots of everybody. Okay, let sigma 1 denote this diagonal matrix. Then this thing here is sigma 1 squared. Okay, and if I write sigma 1 to the negative 1, what I mean by that is sigma 1, I'm sorry, you take the negatives, you take the lambdas to the negative 1/2. Okay, so just a notation. Okay, everybody all right? Try to hang in there. Okay, so we've got this matrix V. Okay, these are all these things are pieces that are going to go together to make our singular value decomposition. Okay, so here we go. Let V1 denote the matrix consisting of the first R columns of V. Okay. So remember, V was a an n by n matrix. V was an n by n matrix, and we're going to take the first r columns. Okay, the first r columns, we're going to call that thing V1, and then the remainder we're going to call V2. Okay, and V2 denote the remainder. Now think, the columns of V1 are eigenvectors of ATA, right? I mean, the columns of V are all eigenvectors of ATA, right? These are the guys that are the eigenvectors of ATA with the non-zero eigenvalues. Okay, and they're orthonormal, right? Because V was an orthogonal matrix. Right, and there's R of them. So the R columns of V, right? The R columns of V are orthonormal eigenvectors of ATA with non-zero eigenvalues. Okay, so they form an orthonormal basis for the range of ATA. Right? Okay, and the columns of V2 form an orthonormal basis for the null space of ATA. Right? Because these are the guys that, right, they're all in the null space. Okay, so let me, so notice, right, this V was orthogonal, right, so V times V transpose is the identity matrix, right, V times V transpose, right, if you're orthogonal, you multiply yourself by your transpose, that's the identity, your transpose is your inverse matrix, right, so let me write it like this. This is V1, V2, V1 transpose, V2 transpose. Okay, because V was on the left V1 and on the right V2, and I'm just going to transpose it here. Okay, so I'm just splitting up V into its two parts. Okay. If you work it out, this turns out to be the same thing as V1 transpose plus V2 transpose. I hope you believe that, right? That if a matrix can be split up in this way, then when you multiply, you get this sort of thing. You can see it. You can see it, right? Okay, so now, right, remember that this thing is a null space of A, right, from this thing, from 1 here, right, from our warm-up exercise. Okay. So what this tells us is that if you take AV2, well, everything, all the columns are going to get killed by A. So you get 0. AV2 is 0. Right? Because these guys are a basis for the null space of A. Okay. So what does that give us? If I take A times the identity matrix, well, that's going to be A times this thing. Okay. But AV2 is 0, so I just get AV1, V1T. Okay. Okay. Now I do something funny. I insert sigma 1, negative 1, and sigma 1 itself inside here. Okay. Right. You got these two diagonal matrices, sigma 1 and sigma 1 inverse. They multiply to the identity. Okay, and this turns out to be the compact singular value decomposition. Okay, so this is sort of like the first step, right? You get some way of splitting up A into this product of three matrices. And we'll use this to build the actual singular value decomposition next time. Okay. I know it's been hard going. Go home and look at it. Go home and look at it, please. Okay.